Okay, so let's dive in here. So this question is related to question 6. So I want to show the lattice of subgroups of Z36. So someone give me a subgroup of Z36. Someone give me one of the most obvious subgroups of Z36.
The trivial subgroup?
Yeah, so there are the two kind of most trivial subgroups are Z36 and just the, I'm just going to write like that, the identity subgroup. So what are some less trivial subgroups? So actually, I should write this as the set generated by the identity there.
The set generates by 2?
Yes. Also the set generated by 3. Cool. The set generated by 4, that works too. Oh, actually, I'm doing this the opposite direction from, so I'm going to erase these. So should have 2 and 3, and then someone said the set generated by 4. For the group generated by 4, good. What else? Groups generated by 6. Cool. Group generated by 9. Someone put in the group generated by 18. And am I forgetting something? Am I leaving anything out? Yes, cool. 12. Thank you, Ben. Yes, cool. So this right here is a not particularly pretty way for drawing the lattice of subgroups of Z36. And so the subgroup order, the fact that something is a subgroup of another thing, I drew out these connections to mark that. What is the relationship between these guys? So we could also think of this as 1. And this is 36. Yeah, so either 1/3 or 1/2. But that's kind of coincidental to the fact that we're dealing with 36. So basically the generators are, as I go down, so if I were to start from the bottom, as I go up from the bottom, it's just whatever divides. So actually there should be this connection as well. I did this kind of awkward staggering just because the wording of the question says something like do it in order of the size of the groups. It would probably look a bit more natural to do it in order of the number of powers of, sorry, the number of elements in the prime factorization. So 4 right here is 2 squared, so it has 2. So it's kind of on this second generation from the top. This guy being the 0th generation. These guys being the first generation because their power is 1. Then we have 6, and then we have 9, and then 12 and 18. 12 and 18. These guys are both powers of 2. Yeah, these guys are both. So this is 2 squared times 3. This is 3 squared times 2. So these guys are all power, or prime factorization has 3 elements. And then these guys combine to 36, which has a prime factorization of 4 elements. And this happens to just be the identity, just the 0 element. Does that make sense? This guy right here is, again, Z36. So this right here, because this, what's the cardinality of this set? What's the cardinality of this set right here? It is 18. So Justin was right there. The cardinality of this set is 12. So that's why when I wrote it the first time, I staggered it down slightly so that it would follow the request in your problem 6, I think it is, that it be ordered in terms of the size of the subgroup. But this, I highly doubt that you would get anything penalized for this because it's still basically ordered that way. Cool. Any questions about this? Okay, so let T sub 2 be 2 to the n, where n is an element of Z. So someone give me a few elements of T2. Someone give me a few elements of T2. Yes, 2 is definitely an element of T2. So two is an element, 4 is an element, right? I can just pick n equals 2. I can pick 8. So this guy right here, this is 2 to the 1. This is 2 to the 2. This is 2 to the 3. If I go down an element, I get 2 to the 0. If I go down another element, I get 2 to the -1. So that's 0. Oh, sorry, this is 1. This is 1/2. And then it keeps going in both directions. So this is the group, the powers of 2 that that T2 is operating on. And my operation is multiplication, right? So is this a group? So first off, whoopsies. Yes, cool. So is this a group? Justin correctly said yes. So what do I have to do to actually check that it's a group? What axioms do I have to check? Yeah. So this guy is closed under star, and let's check that. So we have 2 to the n times 2 to the m is equal to 2 to the n plus m, which is also an element of t to the t sub 2. So that works. Okay, cool. So does it have an identity? Well, what is the normal multiplicative identity? It's 1, or 2 to the 0 here. So identity works. Does it have an inverse? So 2 to the n and 2 to the negative n. If I multiply 2 to the n times 2 to the negative n, I get 2 to the 0 is 1, so that works. And then it is associative because multiplication is associative. Right? Cool. So what is the identity? We answered that in the process of proving that this is a group. Now, t to the 4, someone list off some elements in T4, T sub 4. That right there is not an actual sentence, but so let T4 equal this. Is it a subgroup? 1, yeah, cool. So, 1, 4, 16, 64, and then also good. So 1/4, 1/16, blah, blah, blah. Going out to infinity in both directions. So I'm going to draw this closer. So this is what this looks like. So is this a subgroup of T2? Yeah, it is. It's a subgroup, and it corresponds to the 2n. So T4 it's just the subgroup of them such that it is an even power of 2. Cool. Obviously, it still has the inverses paired up. It still has the identity. It's still closed. Blah blah blah. So, what group would I get if I were to look at the group generated by 2 to the 6n and 2 to the, actually, let's just do 2 to the 6 and 2 to the 8. What group would I get using those two as generators? Do you guys know what get what I mean when I say that, using those two guys as generators? Yeah, exactly. So that's exactly right. We would get 2 to the 2n. So if I get, so 2 to the 6, 2 to the 6 gives me, generator would give me anything that looks like 2 to the 6n, and 2 to the 8 would give me anything that gives me 2 to the 8n. But then if I were able to, or if I can manipulate these two guys, I'm just going to get, basically I'm just going to get the least common multiple of these two. Sorry, not the greatest common factor of these two. Because I can do 2 to the negative 6 times 2 to the 8 is equal to 2 to the 2. And then I can just use this to generate all the elements of this, all of the elements of this, and many more elements. And this is just going to follow as a consequence of the Euclidean algorithm. Have you guys worked with the Euclidean algorithm before? Have you guys done anything with the Euclidean algorithm before? I did it when I taught discrete, and if you guys have done any number theory, then you definitely would have done it. Okay, cool. So basically, you can always manipulate these guys to get down to your least common multiple. And if you have something that looks like a times m plus b times m, that's always going to equal c times the GCD of mn. So you can always get, whatever you get is going to be a multiple of your GCD, and you can get your GCD. Any other questions relating to this? Okay, so what is an isomorphism, and how do we prove that a given mapping is an isomorphism? So just what is the definition here? Yes, exactly. It's a bijective homomorphism, which is what I put down here. A quick note that will prove useful in your, while doing your exam. The inverse image of a bijective function is also a bijective function. So use that as it comes up. People list off some properties that can easily tell you that there is not an isomorphism between two groups. Yeah. So if the size of the two groups is different, then clearly they're not going to be the same group. Other things? Yeah. If it's commutative or not is another easy giveaway. Anything else? Yeah, the number of generators. Actually, I think that those three are all of the so cardinality. So I did cyclic versus not cyclic, but that is the finding the number of generators for the group is actually just a more general way of doing that. So I will change this to number. Cool. Another thing is you can actually just like find one element in G1 and show that it can't map onto any element in G2. That comes up sometimes. So using some of these ideas, why are these not isomorphic? So A4 is the alternating group on 4 elements. It has 12 elements in it. So how do I know? Hint, it's one of these. It's one of these things. What do you guys know about the alternating group? Well, one of the things that you guys should know about the alternating group is that it's not abelian. Yeah, so it's also not going to be cyclic, but the easiest thing is it's just not abelian. These guys are abelian. So this is also not going to be a cyclic group. It has you need 2 generators to generate this group. So not just one, but A4 is not abelian. This guy is abelian. So Z4 versus Z5. This one should be easy. Yes, they're different order. So they are clearly different groups. Z8 versus Z2 to the third. So Z2 to the third, I'm just saying Z2 cross Z2 cross Z2. So what is the easiest way for this? Yeah. So Z8, this guy. This guy is cyclic. So it has 1 generator. This guy has 3 generators. The most natural ones are 0, 0, 1, 0, 1, 0, and 1, 0, 0. You can pick different generators, but these are the most natural ones to go with. Just like this guy, you could pick 7 instead of 1, but so give a permutation of Z20 of, oh, sorry, this should be S20. S20 of order 30. Any suggestions? Yeah, a 6 cycle with a 5 cycle works. So let's do 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11. This guy right here is going to be a permutation subgroup of S20 such that it'll be order 30, because this guy is going to run through, every time I go through 6 cycles, it's going to get back to the start. And this guy, every time I run through 5 cycles, it's going to get back to the start. So it's basically like I'm doing Z5 cross Z6 when they're independent of each other, which is equal to Z30, because yeah, a 10 cycle and a 3 cycles also works. So basically, (15) and 2 also works. So the core of what we need is we need the least common multiple of our disjoint. It doesn't actually even need to be that they're relatively prime. So if we were to do, so I'm responding to Justin's comment here. Justin said that if they're relatively prime, it works. If we did 1, 2, 3, 4, 5, 6, and then 7 all the way to 16. So this guy is 10 and this is 6. It would still be a subgroup of order 30. What we need is the least common multiple of our disjoint permutations. So like this guy and this guy, or this guy and this guy, or if I had a third one here, say 12, 13, I would need the least common multiple of them to equal 30 of the size, least common multiple of the lengths of our disjoint permutations. Does that make sense? Does that make sense to people? Ooh, so if they are relatively prime and they are multiplied together to make 30, it will work. But we don't need it to be that. It's a little bit more general than that, because if the least common multiple of their lengths is 30, then that is a slightly more general case. Just like this 6 times this 10, the least common multiple of 6 and 10 is 30. But okay, yeah. And so this is I think it's question 4 that this relates to. You're going to basically be asked to prove this property, right? No worries. You're basically going to be asked to prove this property, and okay, problem 3. And then do an application of it. I think it's you're supposed to get some group of order 70. So basically you're just trying to find strings that multiply, whose lengths their least common multiple is going to be 70. So pick your favorite collection of string lengths that adds up to, or that adds up to less than this number, right? And that's going to be tied into you're proving the impossibility for part C. So, and multiply to this. So the easiest is just to do the prime factorization of it and then go through. So someone's first instinct here was 2 and then, 6 and 5. The thing that is going to take up the least amount of space here is going to be, not quite the prime factorization. In this case, it is the prime factorization. So here it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this guy right here would, in the end, be the 430. It would be the simplest case. The case that uses up the fewest numbers, like the shortest to right thing that solves this. In general, it's going to be not quite that. So if the prime factorization is 2 to the a times 3 to the b times 5 to the c, blah, 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 then you're just going to go with the highest power there. Because if we had 1, 2, 3, 4, this guy would just boil down to a 2 cycle. But if we had 1, 2, 3, 4, that would be a multiple of 4. That whatever the cycle of this whole thing is has to be a multiple of 4, versus this guy only guarantees it has to be a multiple of 2. Does that make sense? And also, obviously, the elements of these different cycles have to be disjoint. Does that make sense? Cool. That is the extent of problems that I had set aside to cover. And I think it goes over most of them. It doesn't touch 2, because that's basically just a computational one, but it covers all of the other ones. Do people have any other questions that I can answer or that I can try to answer? I can't actually guarantee that it won't kind of be too much regarding the too much information regarding the exam, but if not, anything? Okay, I'm going to stop recording.